Welcome everybody, it's Mrs. Hofferberth. Let's talk about covalent bonding. In a covalent bond, electrons are being shared between atoms. And we can think of this very simplistically in terms of our Lewis structures. So for example, if we take two fluorine atoms, each with 7 valence electrons, and we bond them, we can think of this bonding as occurring between these two unpaired electrons, forming F2. And by sharing those valence electrons, now each fluorine has a full octet or a full valence shell with their electrons. When we write these Lewis structures, non-bonding or unshared pairs of electrons are represented as dots, and our bonding pair is typically represented as a line. So you need to remember that a bond represents 2 electrons. If we take a look at oxygen, we see that there are 2 sets of unpaired electrons, and so bonding in the oxygen molecule can be thought of as sharing of 2 pairs of electrons, and this forms a double bond. Again, non-bonding electrons are represented as individual dots, but now I've got 2 pairs of electrons shared between the 2 atoms, so I have greater electron density between those 2 atoms. Nitrogen, similarly, with its 5 valence electrons, needs to share 3 of those to fill its valence, and so it will form a triple bond. So this is a very simplistic way of thinking about bonding. But what's actually going on to hold the molecule together? What's this sharing? How does that accomplish this? What's really holding all atoms together in all types of bonding is attractions between positives and negatives. This is Coulomb's law. So there must be something that's positive and something that's negative that can be attracting to one another in order to have an actual attractive force. Electrons are negative, protons are positive. It's the protons from the nuclei and the electrons in the bond that are actually attractive. If you think about hydrogen, which is our simplest element, it has a single proton and a single electron. So as I bring these 2 hydrogen atoms close to one another, what happens is the electrons begin to be attracted to both nuclei. So you've got 2 electrons being attracted to 2 protons. This forms the bonding attraction. And if we look at the energy associated with this, energy is related to force because energy is force times distance. And so that means that the energy associated with Coulomb's law is kq1, q2 over r, that distance between the 2 nuclei. This energy, when things are infinitely far apart, or farther than our attractive forces can actually have an attraction, is basically 0, because I'm dividing by an infinitely large number. And so the potential energy when atoms are really far apart is 0. But then as the atoms get closer and closer together, you start having attractive forces. And that energy is, we think of it as negative because energy is being released due to those attractions. They are more stable. And so as the atoms get closer together, we start seeing a decrease in the potential energy of the system. And so let's draw some of these closer together and closer together yet. And so we see this attraction take over in terms of the energy. But then something interesting happens. As we force the atoms even closer together, all of a sudden, the energy is less negative, less stable. It starts to skyrocket, and it becomes what is effectively infinite. If you think about this, what's happened is we've gone from positive and negatives attracting electrons and protons, attracting, to being so close that I'm trying to push my protons, my nuclei, on top of one another. So now those repulsions between the positive charges in both nuclei take over. And so on a very, very short distance between the nuclei, the energy just shoots and becomes positive and less stable. This means, these guys are on top of one another. This means that the sweet spot is that minimum in energy. That minimum of energy is our average bond length. Because the atoms are actually vibrating, they'll actually be a little longer, a little shorter, a little longer, a little shorter, but they're going to stay in that energy minimum while they're bonded. So what's holding the atoms together in a covalent bond? That sharing of electrons, yes, but it's really the attraction of the electrons in the bond for the nuclei that are part of your molecule. So what can we learn and what can we see and read from potential energy diagram like this? Well, let's draw one to start with. When I look at these, like we said before, you can see an average bond length. And you can also see how stable this molecule is when it's bonded. This is effectively the bond enthalpy. How much energy would you have to put in to break it? It's like going backward. How much energy would you have to put in to break this bond? So for something like an attraction between two atoms with a single pair of electrons, you'll be able to find your average bond length and get a feeling for the strength of that bond enthalpy. If you then take, instead of a single bond with 2 electrons doing the attraction, and you move to a double bond, now you have 4 electrons between your nuclei. If you think about this, we've increased the charge. We're going to increase that attraction and that difference in energy upon bonding. And again, if you look at these, we do indeed see that the average bond length is shorter for a double bond than it is for a single bond. And we also see that the bond enthalpy, or the strength of the bond, is greater. We have a deeper well. So the amount of stabilizing is greater, and the amount of energy necessary to break the bond is greater. If we switch to a triple bond, it's even more pronounced. Here again, I have now 3 pairs of electrons. So my charge in my Coulomb's law expression is much higher than it was. Because I have 3 pairs of electrons doing that stabilizing, so you get an even shorter average bond length and an even stronger bond that we see reflected in the bond enthalpy being larger. Remember, bond enthalpy, the breaking out of that bond, is always going to be positive because you have to overcome the attractive forces. Whereas when you go to make a bond, you will always have energy be released because we have a new attractive force. We have lower energy than when we started. So in sum, covalent bonds are about the sharing of the electrons. We can see that in Lewis structures, and we can also understand why they form by recognizing that we have an attraction between the electrons in the bond and the protons in the nuclei. When you go and look at a potential energy diagram for covalent bonding, the depth of the well that you see corresponds to the bond strength or bond enthalpy of your bond, and the relative position on the x-axis corresponds to your average bond length. That lowest energy, that minimum of energy, representing where bonding is going to be occurring.